Alright, question 7. We are now looking at a solar cell and we have a graph which is showing us how the current produced by the solar cell is related to the potential difference across it. Okay, and we're told that this is happening when the light intensity on it is 450 watts per square meter. Okay, so first part of the question, we need to determine the power output when the potential difference is 0.5 volts. Okay, so if we're talking about electric power, the equation that we're going to want to use is that the power is equal to the current times potential difference. Okay, so we know that the potential difference is 0.5. So what we need to do is to use our graph to see what value of current is at that potential difference. Okay, so what the marker will be looking for is that you have actually drawn a line physically on your graph starting at 0.5 volts and going up to check what the current is at that point. Okay, so the current there is looking pretty clearly to be 0.9 amps. Okay, so from the graph, the current there is 0.9, so we then just need to do that simple bit of multiplication. 0.9 times 0.5 gives us 0.45. Okay, so the power output there is 0.45 watts. In 7.2, we've got to draw a sketch graph to show how the power output of the solar cell varies with the potential difference between 0.1 volts and 0.5 volts. Okay, so if we go back to here, between 0.1 and 0.5, the current is staying the same. Okay, it is a constant value of 0.9 amps. Okay, so as the potential difference increases, the power is equal to the current times potential difference, and this is staying constant. So in other words, the power should just be directly proportional to the potential difference. Okay, so there will be a power at 0.1 and there will be a power at 0.5, but what we're looking for is that there should be a straight line in between. We're not looking for you to mark any values on, we're just looking that you understand that relationship. So it's a straight line with a positive gradient, and because this is starting at 0.1, there is already some power. If the graph had started there at 0, then it would have started at 0 power as well. Okay, but we don't need that bit. All we need there is that to gain our marks. In 7.3, we're told the maximum power output of the solar cell is 0.52 watts. We've already been told the light intensity already is 450 watts per meter squared, and it has an efficiency of 0.15 at the maximum power output. So we've got to calculate the area of the solar cell. Now, there are lots of different ways that you could use this information to get to the answer. This is one suggestion for how you could do it. So I'm going to start with the light intensity is 450 watts per square meter. Okay, so what that means is for every meter squared, the input power is 450 watts. Okay, so I'm told the efficiency is 0.15, so then the output power per meter squared is going to be 450 times 0.15. Okay, so per square meter of solar cell, 450 watts are going in, and 0.15 of that is coming out. So 450 times 0.15, I am going to be getting out 67.5 watts for every 450 watts that go in. Okay, so that's per meter. Now what I actually know is the maximum power output of the cell is 0.52. Okay, which is obviously a lot smaller than the 67.5 I'm getting per meter. So if I take my 0.52 and divide that by the 67.5, that should tell me the area in meters that I've got. So 0.52 divided by 67.5 means I have got an area of about 0.0077. And again, there are more decimal places, but 2 significant figures is a reasonable amount to round off to. So I'm going to put in my final answer there, 0.0077, or you could convert that into standard form, that's 7.7 times 10 to the minus 3. Question 7, we've got a household who has 4 of these solar cells. Each of the solar cells has a resistance of 0.78 ohms. Explain how the solar cell should be connected so that the total resistance is as low as possible. Okay, so the idea here is that you remember there are 2 alternatives for connecting things up electrically. You can connect them up in series, or you can collect them up in parallel. And hopefully you've remembered that if we connect things in series, one after the other, so if I had the 4 solar cells like this, then putting them in series basically means their resistances add together. So I'd have 0.78 plus another 0.78 plus another 0.78 plus another 0.78. So doing it that way in series would make the resistance larger. So that's not what you want to do. Okay, what we actually want to do is the opposite. We want to put these 4 solar cells in parallel with each other. So parallel, they go side by side in separate loops. Okay, so that would be the arrangement that would actually give us the lowest resistance, because what I've done there is I've created multiple pathways. So any current coming in has got a choice of going that way, or it can come in and go through that way, or it can come in and go through that way, or it can go through and go that way. So those multiple pathways create lower resistance.